I'm not going to.
It's all the same. Karate, jiu-jitsu, sumo wrestling, boxing, they're all the same. Nothing different about it. Except one's called a sensei, one's called a dojo.
Wait, what's your little leader?
My leader.
What's your little leader?
My leader.
What do you call him?
Just
Sensei?
no, just professor.
Professor.
Do you bow?
This professor's gonna kick your
We don't
butt.
bow. I'll show you what we do. What we do is this thing called just a slap and that. So it's just like this, and then usually that's after we're done sparring or before.
Oh.
So that's what
Is
we
that
do
with
to
everyone?
start.
A slap and dab?
Yeah, well,
Yeah, I can demonstrate.
Why
Pretend
don't
I'm
you do
your
like
professor.
why don't you do like bringing in professor?
well, yeah, that's kind of what it is. I mean,
It's like the COVID.
well, after class we get in a line, and we just like
Go down
slap and dap and just do something like that.
Or
And we'll
slap
move
dab
on.
tap.
Slap that down.
Slap dab tap. I like the slap dab tap.
Yeah, but well, we'll also say
SDT.
we'll also say oos, which means
Oos.
SDT.
it's a Japanese word. It
Oh.
That's
easy.
Oh, that's not a good look.
And that's the terrible word.
SDT.
Alright, I mean, it's
Slap dab.
could be mistaken.
And then what do you say? Ooh.
Oos. It's a Japanese word that just means perseverance.
Goose?
Do you say it with like some grunt, like?
You can if you want, but it's just more of like a camaraderie thing we
Like-
have. Kind of like how the football team will like sing
Or grunt?
the fight song after like every practice.
Wait, you have a fight song?
No, the football team. You know,
What-
it's
what
like
is it?
we the sons and daughters
Oh.
follow. You know that one? It's kind of.
Why do they say daughters? There's no females on
I
it.
know.
Yeah, no. but
Manager.
It's like the whole.
we the sons and daughters follow. No, but
Oos.
Ooh, it's like goose, but without the
no, it's
G.
just like oos.
Oos. Yeah, let's try it. Slap dab.
Oh,
That's pretty good.
Yeah. You should come by sometime and get to experience the family that we have.
High potential ringworm on those mats.
oh.
No.
What's your professor?
So, right now we have two. One of them left, but it was a Brazilian jiu-jitsu teacher that's actually from Brazil, came to America. When he got like his
What's his name? Hoist Gracie?
no,
Oh.
but he after a while he left to start his own gym because he got like his work permit. But right now we have this guy named Rayford King. He teach mixed martial arts. Rayford King.
I think I grew up with Rafer.
He works at Big
SDT?
Sky right now.
Did he grow up in Missoula?
I think so. Yeah.
Ask him if he went to Covenant Church growing up. Do you know his dad's name?
No.
Wow. I think I know.
Yeah, that's a son named Quincy.
Oh.
I wouldn't know Quincy, but I would know. This would be like about 35 years ago.
He has darker hair.
Yeah, 35 years ago was the last time I saw this child. Ask him if his dad is Tom and if he went to Covenant Church.
Okay.
That's your professor?
Yeah, and he's a brown belt. We also have Coach Komodo. He kind of does all the
Coach who?
Komodo.
Komodo.
Like
That's his,
Komodo
like-
Dragon.
Yeah, I know that's his nickname.
Oh.
There you go.
What's his real name?
I think it's like
Steve.
I think it was like Jones something. I don't know.
Oh, I want to be Coach Komodo. I want to be Professor Komodo.
Komodo.
Sounds cool.
We could call,
You should come on Sunday at 2 p.m. We do free classes.
free classes. And now you know how to, like, introduce yourself to Professor Komodo.
Ooh.
Slap,
What
tap,
do I say?
tap.
Oos.
Ooze.
Ooze.
O S S S S S S S S S.
Ooze.
No, not ooze.
Oos.
Oos.
It's like
Goose.
without a G.
Goose.
Oos.
Whatever. You should come though. I promise it's a lot of fun, and the people that train there, they don't want to like hurt you or anything.
Yeah.
Don't hurt you too bad.
Ricker actually came and he had fun.
Everyone's, yeah.
So did Nick, right?
Nick came, but it was only like me, Nick, and Rafer there.
Oh.
No, it was lots of fun though.
Cool.
Yeah. Nick, sorry.
You wanna keep talking about ooze?
Oos.
Do you want to talk about math now, or?
I do.
Okay.
I want to talk about sectors of circles. A
Yeah.
sector of a circle is a part of a circle. S does not stand for sector. S stands for arc length. Okay. So then you have a central angle and you have a radius. The radius for this formula, this would be when when theta is in radians. Okay. Then if you're in degree mode, there's another formula which would be theta over 360 and then times 2 pi r. Okay. And that one actually makes a lot of sense because 2 pi r stands for what formula? Circumference. And then theta over 360 represents the fraction of the circle you're dealing with. So if you were, because remember arc length S is just a distance of the circumference. And so if theta was 90 over 360, right? If theta was 90 over 360 would be 1/4. So you're 1/4 of the circumference.
Wait, S is sector? Or in the bottom one, S is sector?
No, S is always arc length.
Oh,
A sector just means like it's part of the circle, like a piece of the pie, if you will. Slice right there. That's the whole thing is the sector of the circle. S just stands for the arc length, which is the fraction of the circumference. So this formula right here would be, this represents how much of the circle, right? So like 90 out of 360 would be 1/4 of the circle. 1/4 of the circumference would give you this distance from there to there for the arc length. So that makes sense when it's in degree mode.
So the top is for radian and the
But
bottom.
the top is radian mode, which isn't as clear. But so if you are in radians, then you use that.
And the bottom is degree mode.
Bottom is degree mode. Yep. So on the test, I would probably give you these formulas. You would just have to know which ones to use. Because then we tack on 2 other formulas, and those are the area for the sector. Well, there's 3 total formulas, but the area for the sector of the circle is r squared theta. Sometimes they use capital K for area in math, or A, but in this case you're using K for area. So K equals 1/2 r squared theta. That is, again, when it's in radian mode. Okay. When it's in degree mode, K equals theta over 360. So a fraction, right, of the circle. And then you just do your equation, pi r squared, for the area of the circle. So those are your 4 formulas. This is for sectors, this is for area. Then there's one other area formula that does not entail, doesn't entail any of the angle measures. It's just 1/2 RS. So it's neither radian nor degree mode. It is just simply when you know your radius and your arc length. So this is you don't have to know if it's radians or degrees because it doesn't deal with the angle measure. So I'll give you those 5 formulas, and then you can just figure out what to do with them based off of the information given. So on the mid-chapter assessment or test, if I forget to put them on there, just remind me and I'll throw them up there for you. So some examples would be if a sector of the circle. The sector of the circle has radius is equal to 5 and theta is equal to 3. Now, when I say theta, they define it more, they say a central angle. So the central angle is 3. And then you want to find S equals unknown to K equals unknown. Now, how do you know if theta is in degrees or radians?
The degree label.
Yeah, degree label, or they'll tell you it's 3 radians. If they don't tell you, you would look for the degree symbol or non-degree symbol. So no degree symbol, we're going to make this this is going to be radians. So if it's radians, we're going to come back over here and we're going to say, okay, this is our radians, and then this one is our radians when we're looking for the arc length and when we're looking for the area. And all it is simply plugging in to the equation S, because we want to find the arc length, is equal to r theta. So 5 times theta would be 3. And so the arc length would be simply 15. Okay. And again, what the arc length is, it's a distance, it's a fraction of the circumference.
So wait, where is K on the circle?
K is just the area of the sector of the circle. So K represents the area of like the slice of the circle.
Okay.
So in this case, K, we would go, okay, if we're in radians. Now, if you already know S and you know R, you could just use this K, right? You could use K equals 1/2 RS, because you know R now. Or you knew R in the beginning and you know S now. Or you can go R squared theta. It doesn't matter. Both will yield the exact same answer for you. So if we go 1/2 R squared theta, 1/2 R squared, and then theta would be 3. So K would be equal to 25 times 3, 75 divided by 2, 37.5, 37.5. Okay? So that's the basics of some of those. And here's one though. Okay, a sector has perimeter is equal to 12 and area equals 8. Find all radii. 2 eyes on radii. Find all possible radii. Okay. So this information, you're given a sector of a circle has a perimeter 12 and an area of 8. Find all possible radii. So look over here. Again, the perimeter is for the sector. So let's draw a circle, okay, here. When it talks about the perimeter, it's referring to the perimeter of the sector of the circle. So it's not referring to the perimeter of the circle. So you are looking at something like this, this, and this. So what makes up the perimeter of the sector of the circle? Well, it would be a radius, and a arc length. Not sector, but arc length, right? Yeah, S. So to find perimeter, right? Perimeter is just add up all the sides. So in this case, it would be R plus S is equal to 12. Then the area formula, since we're dealing with R's and S's, maybe not great to go area is R squared theta, because then we introduce another variable theta. So the area formula we'd probably look at is one that uses R's and S's. So like this one, K equals 1/2 RS. So what we know is over here, we have another formula, K equals 1/2 RS, which is 8 is equal to 1/2 RS. All right, how do you solve equations like this?
Set the, or solve for S or R.
Yeah, solve for S or R and then
Substitute.
yeah. So it's not a system of linear equations because we have R times S, but it's a system of equations which should be very solvable. So I would maybe say S is equal to 12 minus 2R for that one. And then 8 is equal to R times 12 minus 2R. Like that. Now it says find all possible radii. And you know you're going to have more than one radii, or more than one radius, potentially, because you're going to end up with a quadratic here, right? Oh, you got 4? Good.
4 and 2.
And 2. Okay. So those are your possible radii.
So then would the arc length equal 4 or 2?
You're just finding the radius, so you
Oh,
could.
you don't need to.
It would just depend on which radius you use. If you use a radius of 2, the arc length would be 8. If you used a radius of 4, the arc length would be 4. So. Okay, so then the other thing that we'll talk about is this thing called apparent size. Okay, and apparent size is like when you look at a planet and you judge the size of that. We can't judge the size of it because there's nothing else to reference it to, but we can look out at the planets and judge the size of an object. We perceive the object to be smaller when it is farther away. So when the sun is much larger than the moon, for example, the sun is much larger than the moon, but we perceive the sun to be about the same size as the moon because the sun is so much farther from the earth. Thus, how big an object looks depends not only on its size, but also on the angle that it subtends at our eyes. Subtends, if you recall from geometry, it's okay if you don't, but that word subtends would mean this. If you are here and you have a planet out, actually here and you have a planet out here, subtends means that you'd have 2 tangents like that going to it. So the apparent size, okay, the measure of the angle is called the object's apparent size. So the apparent size is based off of this angle measure right here, theta, okay? Now, what we can do is use this concept to think about the diameter, if you will, of a planet. And the way we can do that, maybe I should move it closer, but we can look at this. This is, if you drew a spot like this, and this is going to be okay. So if you have this huge circle like this, and there we go, that's okay. So if we have a huge circle like that, and you're in the center looking out at a planet, you have a central angle theta. This angle here is called our apparent size, okay, of the object. So when they talk about the apparent size, it's referring to the angle, the central angle. Then you would have a radius to that, and then out to the spot where it's subtends, where it's tangent there. And then this piece right here, it's an approximation of like the diameter of that planet. And then it's also, though, from here to here, this would also be called an arc length, right? That would be S for your arc length of the green circle, right? Because if you erase the planet, say, okay, I would just be looking at an arc length here, but then you include the planet that you're looking at, it now becomes like an approximation of the diameter. So you're using all the same equations. It's just a look at something with that they can use to approximate. And you can measure, like when you think of apparent size, if you've ever been traveling, I remember traveling as a little kid, and you're like going to a big city, and you can see way off in the distance the skyscrapers, and it's like always exciting. And you're getting closer, and the skyscrapers start getting bigger because the apparent size is changing because the angle measure is changing. So that is what apparent size is, and you'll have some problems. It'll talk about the apparent size is, and again, the apparent size is referring to the angle measure. So the apparent size of something is, point blah, 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 blah degrees, like 0.003 degrees or 0.003 radians, because the apparent size when you're looking at a planet will be a tiny, tiny angle measure looking out there. So that is apparent size. So I think that's enough for now. For you to slave away. Have we graded? We haven't graded anything, have we? Okay.
Did we grade 6-2?
I don't think we did. We'll grade 6-2 tomorrow, and then 7-1. We should grade tomorrow, but people are gone. Why don't we grade that on?
Who's gone?
Why don't we grade 7-1 and 7-2 on Thursday?
Wait, who's gone?
Because today Tuesday?
Yeah.
Yeah.
Okay. Thursday. 7-1 and 7-2 Thursday.
Wait.
Carmody and Nick.
Where are they going?
Where are they going?
Yeah.
I don't